Guys, am I audible to you? Okay. So how many of you actually went through the IPO NB notebooks of yesterday's class? No one? Right. How many of you want to give the mock interviews? Okay. Just Prakash. That's it. Fine. Prakash, have you started to revise the concepts? Actually, we'll connect with you afterwards. So what we want to discuss today is naive bias. Okay, Prakash, have you done the revision? The files uploaded. Got it right here. All the files are uploaded. All the files have been uploaded. All the videos have been uploaded. So right here. Right. Anyway. Okay. So I will go through it. Okay. Karthik, are you able to see the files or are they still not showing up? You should be able to see the files. Let me know if you're facing any issues. My files. So this is what we are going to discuss, right? Prakash, I'll let you know. It depends upon how quickly you guys are finishing up with your revision. because no point in taking the interviews if you're not through with the stuff, right? Not done the revision, then there's no point. And before even starting the mock interviews, you have to do the projects, right? You have to do the projects. So because projects is what we are going to discuss in the interviews. And if you are in the deep learning batch, then you have to wait a little bit because it will be a combined thing. Okay. Fine. Okay. So what we have to discuss is two things. One is your knife-based algorithm, and the other one is your anomaly detection algorithm. Yeah. Okay. So how many of you are actually familiar with the knife-based algorithm or conditional probability? How many of how many of you are familiar with this? Okay. Okay. So your knife-based algorithm, it works on your conditional probability. Now, what is conditional probability? Conditional probability. So if you consider heads or tails when you spin a coin, right? If you consider heads or tails when you spin a coin, this is not conditional, right? Because heads is independent of tails, right? It is not conditional. But if you consider a heavy coin or if you consider a biased coin, right? In some way, if a coin is biased, then in that case, the probability is conditional, right? In that case, the probability is conditional that maybe if you're flipping the coin with with the head side on the top and the tail side on the bottom, then it is going to land on tail. Then the coin landing on the tail side will be more as compared to coin landing on the either side, right? This is called your bias condition, right? Where your probability is actually being influenced by something else, right? So probability of A when B is true. This is your conditional probability, right? So the formula for knife base, right? The formula for knife base that we use is something like this. This is the formula that we are going to use in knife base. Now we'll try to solve a small problem statement using this formula, right? But before that, is this much clear to everyone? If you're not clear with the probability and everything, then you have to refer to the statistics video. Right? But anyway, this is the formula. Now, I'm going to give you a small problem statement, and we are going to take a look at that. So this is a small problem statement that we have, right? This is a small problem statement that we have. Just give me 1 minute. I'll increase the size. Right. So this is the problem statement. It is saying that there are two machines, right? Two machines which are what? Which are producing the bulbs, right? Both of the machines are producing at a rate of 30 bulbs. So your machine one is producing 30 bulbs per hour, and machine number two is producing 20 bulbs per hour. This is the rate at which both of the machines are producing the bulbs, right? So in 1 hour, how many bulbs are we producing? Right. In 1 hour, we are producing 50 bulbs. This is what we are doing in 1 hour, right? So after that, what is written is that the total rate of defective product, right? The total rate of defective product is 1% out of all the bulbs that are being produced, right? So 1% is the rate of defective product. So 1% of the bulbs that are being produced are defective, right? So this is your defective part. Now, what is the share of the bulbs that is defective from both of the machines, right? So the share is 50%, right? So machine one and machine number two, they are both equally likely to produce a defective bulb. That is what this is telling you. Now what we have to do is that we have to find the probability that the bulb produced by machine 2 is defective. This is what we have to do, right? That is the problem statement that we have. Probability of the bulb that is defective produced by machine number 2. So now we're going to apply the same formula that we have, and we are just going to plug in the numbers. That's all that we have to do. Just give me 1 minute. Okay. So if we put everything inside our formula, right? So we have P defective machine number 2 will equal to P machine number 2 right? This is what we have. This is the formula that we have, and now we have to figure out are a few things, right? We have to figure this thing out. This thing that we have to figure out is what is the probability of machine number 2 producing a bulb. So the probability is going to be is 30. Your machine number 2 is producing how many bulbs? I think it is producing. I'll show you the screen again. Machine number 1 produces 30 bulbs. Machine number 2 produces 20 bulbs. Right. So the probability is going to be go back. Right. So 30 plus 20 divided by 50. So 20 divided by 30 plus 20. This is going to be the probability. Right. So this is the probability that we have for a bulb being produced by machine number 2. Okay. Now what we have to find out is the probability of the defective bulb. What is the probability that a bulb is defective? So from the problem statement, we know that 1% of the bulbs are defective, right? So if you convert it directly to the probability, it is 0.0. Right, this is the probability. So right here, it's going to go right here, 0.01. So that is what we have. Now, the third thing that we have to figure out is probability that machine 2 produced and it is a defective bulb, right? So since both of the for machine 1 also and machine 2 also, the probability is 0.5. So for that one, it will be 0.5, right? Now, if you put everything into the equation, it will look something like this. And the answer that you will get will be this. So this is how your simple knife-based algorithm is working. And if you want to change it up, if you want to find out the probability of defective bulb coming out, and given that machine 1 is producing it, right? In that case, you just have to change a few parameters here in the formula, and then the approach will be still the same, right? So this is how your knife-based algorithm is actually working, right? So now, here's all this. If you want the notes for this, I think I have the notes for this class also. So if you have a binary problem, because that was the binary classification that we have done, right? In that case, we just have machine 1 and then machine number 2. What if we have multi-class problem, right? Instead of binary, it is a multi-class problem. In this case, what you are going to do is that you are just going to find out all the probability, right? Probability for all the classes, and then you're going to use the simple argmax function. Not you are not going to use it, but the internally what is going to happen is that simple argmax function is going to use, and whichever one is having the highest probability, that is going to come out, right? So that is going to happen. So argmax is just simply getting out the argument with the maximum value. That's all, right? So that is how your naive-Bayes algorithm is actually working. Is there any doubts regarding the naive-Bayes algorithm? Next thing that we have is Gaussian. Yeah, it is. It is conditional probability. Next thing that we have is the Gaussian naive-Bayes. Now, where you might want to use Gaussian naive-Bayes is mostly in the machine learning problems. You'll be using the Gaussian naive-Bayes. You might be using, where do we use the conditional naive-Bayes? The conditional naive-Bayes, it is used mostly in the NLP tasks, right? So we're going to use is the Gaussian naive-Bayes, and the formula for Gaussian naive-Bayes is right. So this is your formula for the Gaussian naive-Bayes, right? So it might look big to you, but basically what we have to figure out is just a few things. So first thing, this C that we see right here, this is representing your class. For which class are you trying to figure out the probability, right? This x equals to v, right? This v is your value, or x is your value and x is equals to v, right? So it's the same thing as x for c, x given c, right? It's just the way it is written there, right? Next thing that you have to figure out is this part. So what is this? This is nothing but your mean, right? Mean for class 1. And then you have to figure out this. This is your standard deviation for class 1 variance. Standard deviation is without the square root, right? So once you have figured this part and this part, then you can simply put the you can because you'll have the value of the class that you are the unknown that you are trying to figure out, right? So this is the data set that you have, right? And these are the two classes that we have. And let's say this is the new data point that is coming in, right? So the value of this is going to go for this v part, right? The if you're trying to figure out the class one, then you're going to consider these blue points, and you're going to find the variance and the mean for these blue points, and then compute the entire equation, and then it'll give you the answer, right? So this is how you are implementing a knife base. Now let me ask you something. So yesterday when I was discussing K and N, so I believe I have not discussed the KD tree and the ball tree, right? Have I discussed the KD tree and the ball tree? Okay, fine. So knife base is clear to everyone, right? Guys, is knife base clear to everyone? Can you guys answer this one? Because I am expecting an answer from you. Just type in yes or no. If you don't want to answer, just type in no. And, no, you cannot use the knife base for regression-based classification because knife base is giving you a probability, and probability will always be between 0 and 1. So therefore, uh, you cannot use knife base for the regression-based regression-based problem, because in the regression case, your output will not always be between the 0 and 1 class, right? So therefore, you cannot use it for the regression-based problems. Going to the KNN part, right? Going to the KNN part. So if you have discussed how the KNN model works, right? So the way KNN model is going to work is that you have it right here. So you have the data points right here. These are the data points that we have. Now, whenever you are training the KNN model, the training phase will include saving of this entire model inside your memory. This is what your training phase of KNN model is. Now, if you want to test the model, right? If a new data point comes in, let's say this red is the new data point, and it is coming in and it is sitting right there, right? It is sitting right there. Now you have decided that now it is sitting right there. Now the way KNN works is that it is going to figure out the nearest neighbors that it has, right? So let's say we have decided that we want to take a look at 3 nearest neighbors. So we're going to take a look at this one, and probably that one, probably this one, right? That was this one. So this is how your model is going to build up. Now it is going to figure out to which class these two belong to which class each of these points are belonging to, right? So whichever class is getting the majority, right? Whichever class is getting the majority, that class, this red class is going to get classified to that class, right? That is how your KNN model is working. Now there are a few problems with this approach. There are a few problems with this approach. So the first problem that we have is that if you have a really high dimensionality in your data, if you have really high dimensionality in your data, what is going to happen is that a new point is coming in. It is sitting right there, right? Let's say this is the new point. Now, the first step, so we know that how the prediction is running. We know for prediction, it is going to look at the three nearest neighbors. We have decided that the value of k we want to give equals to 3, right? This is something that we have decided. But we can visualize this, that this is the nearest point, this is the nearest point, and this is the nearest point. We are able to visualize this, but your system won't be able to visualize this. Your model won't be able to visualize this. What your model is going to do is that it is going to find out the distance between all the points, right? It is going to go through a couple of steps. So first thing that it is going to do is that it is going to find out the distance from all the points. Then it is going to arrange them. After arranging, then it is going to decide, right? Then it has to calculate the class, right? In case of classification, it is going to do the probability calculation. In case of regression, it is going to do the average, right? So you can see that there are a lot of steps that you have to perform before you are able to get the prediction, right? After this, you're going to get the prediction, right? So this is the problem with KNN model. Now, in order to fix this problem, what we can do is that that approach that we have seen, where it is calculating the distance between all the data points that it has, that is called your brute force approach, right? Now we're going to look at something more sensible, right? Something which researchers have done. So they have done is that they came up with two models. One is your KD tree, and another one is your ball tree. So just by the name itself, you must be able to understand that we are going to do something with the trees, right? So what is going to happen is that your data set that you have, it is going to get divided into different parts. Using a decision tree, you are going to divide your data set, right? And after your data set has been divided, not a lot, but like just enough, right? Then what is going to happen is that whenever a new point comes in, this is a new point, it is coming in. So in decision tree, we know that the training phase is a little bit complex, but in terms of testing, it is just going to go and decision tree is just going to put it in some in one of the either sides, right? So let's say this point is coming in, and this point, it is going in towards this side, right? Right here, this point is lying. Now, KNN model is just going to run on this side. So this has reduced your complexity by 50%. And if you go into the decision tree even further, right? If you're at this point, let's say, then you are again dividing it. Then it has further reduced it to around 25 or 20%, right? The processing that is that you need from KNN, that has reduced by quite a lot, right? So this will actually do two things. So one thing that it will do is that it will increase your training time and it will decrease your testing time. Now the effect on the testing time will be very significant, right? In terms of how quickly you are able to get the predictions. Now, when it comes to the ball tree, so let's say this is your data set. What is going to happen is that you are going to get the classification. So let's say this is your one. Clusters are going to get made, right? This sort of clusters are going to get made, and then whenever a new point comes in, let's say X is coming in, and first thing, this X is going to go through the clustering algorithm that you have run. After that clustering algorithm, it is going to sit somewhere, and then there the KNN model is going to run, right? So that is how your ball tree is written. So in terms of ball tree, the training part and the training process is going to be even longer as compared to the KD tree, right? Because clustering will take a little bit more time as compared to the KD tree. So that is how you can simplify, or that is how you can actually improve the KNN algorithm. The brute force method, you can actually add some sort of logic to that, and that is how you can do that. So going back to the naive base, the thing that we have to discuss is what are the advantages of naive base. So can you guys tell me what are the advantages of naive base? Just by looking at naive base and the rest of the things that we have done, can you guys see a few advantages here? So far, what we have seen, see, in case of SVM, in case of decision tree, in case of even linear regression, logistic regression, in case of stacking, we've seen that the equation that we were using, it is quite complex. In case of naive base, equation is very simple. Do you guys agree with me on this point? That equation of a naive base model is very simple, right? Even you are able to do it without using any sort of system, right? So that is one advantage, that the equation is simple, therefore the resources that will be used, they are also minimal, and your training and testing time will go down significantly. That is one advantage of using naive base. Second advantage is that since the equation is very simple, so the interpretability of the model, right? So you can interpret it easily. And the third thing that you have is that the hyperparameter tuning, right? It is almost none. In iBase, there are almost no hyperparameters that you have to tune, right? So that is the third thing that you have. This is the third benefit. And these are all the benefits, but this does not mean that naive base is compromising with accuracy. In terms of accuracy, naive base performs very well. Right? In terms of accuracy, naive base will be giving you very good results, and that is why you are using naive base for simple NLP tasks. Right? The scikit-learn implementation of naive base, that is for the scikit-learn implementation of your algorithms, your naive base will be used. Right? So this is all about naive base. I'll take up the Python implementation of naive base in the next class. I want to discuss now is anomaly detection. So we have not seen the clustering model so far, right? But if I ask you, what do you think of what do you think is anomaly? It is nothing but something that occurs very rarely, right? Or something that does not fit anywhere, right? So if we have a graph like this, these are all data points. And what I am trying to show you here is the unsupervised learning. Unsupervised learning approach to the anomaly detection. We'll discuss unsupervised learning in detail in the next week. But right now, just the geometrically, if I show you, right? If you build one cluster right here, you're building another cluster right here. You're building the third cluster right here. Now this point that you see, it is not fitting anywhere, right? So using the clustering model or using the unsupervised learning approach, this is how you are going to extract the anomalies. A point which is not fitting anywhere is going to be your anomaly. Now this was about the unsupervised learning. Now in terms of supervised learning also we can see anomalies, right? So in terms of supervised learning, if I ask you for an example, what type of example do you think will justify the occurrence of anomaly? Will Do you think engine failure is an anomaly? Guys, yes, no? Prakash, what I am asking is supervised learning. Like in your day-to-day life, can you give me an example of anomaly? So engine failure, right? Uh, 1 out of 10 engines are failing, I guess, or even less than that, right? Because engine failure isn't that common nowadays. As the engines are advancing, as the technology is advancing, the engines that we are getting, they are quite a bit, they are quite reliable, right? So if an engine is failing, it is anomaly, right? Fraud detection. I think fraud is, you can say that it is a kind of anomaly, right? But you can still classify this as a normal classification problem also, but still, uh, you can say that it is an anomaly. Server failure, right? I think this is also an anomaly, right? So if you look at the host engine, they say that their uptime is 99 or 99.9%. I'm not sure, something like this, right? This is what they claim their uptime to be. Now, what this uptime means is that for 99.9% of the time, their server is working. Now, if out of 100%, just 0.1% chance is there that something is going to happen, so that is definitely an anomaly, right? Prakash, are these all examples? Is it clear to you now, like what I was trying to ask, right? Yeah. So these are all your anomalies that you can see in your day-to-day life. Now, if I ask you, the server, let's take the server example. In case of server example, we can also do this in terms of classification. Can we not do this? Classification, right? We can say that server will fail or it will not fail. Class A and class B. Simple. Can we do this in terms of server failure or any other thing? We can also classify this problem as a classification problem, right? So why are we not using the classification and why are we using the anomaly? Why would you use anomaly when you have the classification? The reason is pretty simple. In case of classification, right, right. So you guys are right, but what I am looking for is the word imbalanced. Heavily imbalanced, actually, not just imbalanced. Heavily imbalanced, right? This is what's going to happen if you are trying to apply classification model. Now, classification models, as we have discussed, if your data set is heavily imbalanced, right, you can definitely upscale the data set, but that will, that will mess up the integrity of your data set, right? That will mess up the integrity, and therefore, upscaling is not a good idea. In that case, a new class of algorithms have been developed. These are your anomaly detection algorithms. Now, the anomaly detection algorithm that we are going to look at in this class is going to be isolation forest, right? So if I just by looking at the word isolation forest, this is, so anomaly part is clear to you all, right? What is anomaly and why do we take a look at it, and why we cannot use the classification algorithms on that? Okay. So if I say isolation forest, what is the first thing that is coming to your mind? Right, isolate, and the second thing that you should be noting is the forest part. And now with this forest, a particular model should be coming inside your mind. That is your decision tree, right? So this is why decision tree is so much like, this is why the decision tree is so popular with the interviewers, right? This is why most of the times interviewers are concerned about the decision tree and they'll ask you many questions regarding this. So what's happening inside the isolation forest, or before even talking about the isolation forest, let me show you how a tree can actually remove the anomaly, or how a tree can detect the anomaly. So let's say this is your entire data set. You've done the division. This is your division 1. Now out of all these divisions, right, which one do you think is an anomaly? Let me name them: A, B, C, D, E. This one. Prakash, how is E an anomaly? This is the anomaly, right? B is the anomaly. This one is sticking out, right? The rest of the data is actually right here, right? So even if even if you remove this A, even if you remove this part, right? Even if you remove like this much, even if you remove this much, right? Even then you will be able to build a complete tree, right? Even then you will be able to build a complete tree. So this is the anomaly, this part, or not this entire part, but just this B part. This A is just, I'm trying to show you that even if you remove the A part of this and then that, then also you'll be able to build the tree. But the anomaly is B, right? And how do we like, what did we use in order to judge the anomaly? We used right, but in terms of division, like what are we trying to see in terms of division? What we are trying to see is the ease of isolation. This is what we are trying to see: ease of isolation. So how easily, right? How easily are you able to? Uh, what this ease of isolation is that how easily are you able to decide whether a point is anomaly or not, right? So if I say that this is a decision tree, right? Because this was the extreme case where this first division is giving you the anomaly. Let's say this is the decision tree. On this side, it is continue to growing. It is continuing. It is growing and growing. But on this side, it has stopped right there, right? So ease of division or ease of isolation is directly proportional to how many steps you are going. At how many steps you are able to figure out the final node. That is your ease of isolation, right? That is your ease of isolation. Is this part clear? I think the decision tree should have given you a sort of intuition behind like exactly is happening. Now, means depth. Yes, you can think of it in that way. Depth. So That is our like intuition, like how is it happening. Now in terms of prediction, a few things should be coming to your mind, right? The first thing is, how do you decide? How do you decide the depth, right? How do you decide the depth at which point, like how do you decide the threshold at which point you should be stopping, or at which point you should be considering it as an anomaly, right? This is the question that should be coming to your mind. And in order to answer this question, you are not supposed to decide the depth, right? That is the whole point of supervised learning, right? Since we are dealing with the supervised machine learning algorithm, you will already have the labels, right? You will already have the Y labels for the X labels, right? So your machine learning model is automatically going to just judge by itself. It is going to set the threshold value, right? And that is going to give it to you. Now, whatever we have discussed so far, that was in terms of one single tree, right? But why do we use multiple trees? So that we can have a robust model. In order to have a robust model, we are going to build multiple trees. Now, each tree is going to give you some sort of output. Let's say x1, x2, x3, x4, right? Let's say these are the four outputs that you're getting from four trees, and together four trees are making up a forest. What type of forest? Isolation forest, right? So this is the story so far. So these are the four outputs that you have. Now what you're going to do is that you're just going to take the average and you're going to decide the threshold. That's it, right? And that is how you are going to implement the anomaly detection using the isolation forest. There are other isolation algorithms that also exist. And in the next class, I think I'll take up one more, right? So if you want to read more about the mathematics of this isolation forest, right, you can download the documentation and you can go through the documentation also, but that is not required. Even isolation forest, how many of you had heard of isolation forest before this class? Right, so isolation forest, it's a relatively new model, and even in the interviews, no one is going to ask you isolation forest because most of the times, as a fresher, no one will be knowing the isolation forest, right? So if you want to dig deep into the mathematics, feel free to do that. And one more question. So regarding the SVM and regarding the random forest classifier, and not the random forest, the boosting, right? So SVM and boosting, these two, they are having some complex mathematics, right? You don't need to go into this complex mathematics. So that is why I have not explained the mathematics of SVM and boosting in live class. If you want to, if you want to have an idea of this, if you want to know what type of maths is happening inside it, right? I can make a video for that and I can upload it onto the LMS if you want, right? But in terms of understanding, if you're going into the complex part, I'm pretty sure you won't understand anything at this point, right? So if you want to have that, I can do that. Just let me know, right? Regarding the other stuff, that is it for today's class. And now we're left with the PCA, some few things like AUC ROC, accuracy metrics, and standardization normalization. So these are the few topics, and then we are going to take a look at OOPS concept, and then we are going to spend some time on the projects, right? Any doubts, guys? Okay. So, right. So by next week, our theory part will be done, and we are also going to Naive Bayes classifier. Right. I'm not sure about it. Never read that article. But normally you don't use naive Bayes with regression. I'm not sure when that article was written. Right. Right, guys. Right. So you guys don't have any more doubts. So I'll see you in the next class then. Okay. Thank you for attending.